next talk will be given by Sean Hartnoll. He will tell us about bootstrapping matrix quantum mechanics. Please, 45 minutes.
Okay, great. Thank you. Is the sound working?
Yes.
Yes, great. Okay, thank you. Perfect. So yes, so I want to talk about bootstrapping quantum mechanics. So this is a paper that we just put out very recently. Oh, so let's make this work. Why is this not working? So 1 second. There we go. Perfect. Okay, so that's the paper, and my collaborators are my graduate student Shizhe Han, and Yorit Kritov, who's a postdoc at Stanford. Okay, so let me just give a few words of motivation. So I think it's quite clear at this point from everything that we know about holography that space is not a fundamental concept, but something that emerges from a non-geometric description. And furthermore, we have now very specific models where we know that happens, which are, and in the best understood of these models, we have quantum mechanical theories of large n matrices. So n equals 4 super Young-Mills, I guess, is the most famous, that can produce not only a space-time, but a semi-classical space-time that obeys Einstein's equation. So it has gravity, and it's weakly curved, and it's a sort of a more or less realistic space-time. So we know that's true, but we don't understand how it works. So how do these matrices, how do the degrees of freedom that make up the matrix dynamics, how do they rearrange themselves into this space-time and into Einstein's equations? Okay, so how does this duality really work? So I'm going to be talking about not quantum field theory like n equals 4 super Young-Mills, but actually perhaps what I would consider the most irreducible example, which is matrix quantum mechanics. So in matrix quantum mechanics, there are large n matrices, but there's no space to start with. It's not a field theory, okay? It's just the quantum mechanics of its many, if you like, it's many coupled harmonic oscillators, okay? N squared, a lot of coupled harmonic oscillators. And so there's no space to begin with. So there's no field theory locality that's built in. It's not a field theory. And what that means is that all of space must emerge, okay? We can't somehow use the space that we already have on the boundary to give the space in the bulk. The whole space has to emerge from the matrices. And so to understand this emergence of space, what we'd like to do is solve matrix quantum mechanics. Okay. So people have been trying to do this for a long time. And there are many theories of matrix quantum mechanics. And the simplest one is the theory of a single matrix. Okay. So the quantum mechanics of a single matrix is very special because if you have one matrix, you can diagonalize it, and it turns out that when you diagonalize a single matrix, the eigenvalues become free fermions, and you can just solve the quantum mechanics of the free fermions. This was done at least in the late 70s, and it played a key role in a lot of excitement in two-dimensional string theory in the early 90s. Okay, so this one matrix is pretty completely solved at this point, I think. Well, okay, largely solved at this point. Now, at the other end of the spectrum are maximally supersymmetric matrix quantum mechanics. And so these are the richest theories. And so these have 9 matrices in maximal supersymmetry, and they come in 2 variants. The first one was the BFSS theory of M theory. And then a bit later, there was BMN discovered a mass deformation that preserves the supersymmetry and describes M theory on plane wave backgrounds. Okay, so there's a line, right? At one end we have a single matrix that we can completely solve. On the other end is BFSS and BMN, which are, I mean, I think it's clear that if we could solve those, we would understand a lot about quantum gravity, but we can't solve those yet. Okay, so in this line between one matrix and maximal supersymmetry, there are lots of theories. There are many theories of matrix quantum mechanics that have 2, 3 different amounts of matrices and different amounts of supersymmetry. But as far as I'm aware, all theories that have more than one matrix are not solved yet. And just to be clear, I'm not talking about matrix integrals. This is matrix quantum mechanics. Okay, there is time. Matrix integrals, there are matrix integrals with two matrices that have been solved. But as far as I'm aware, in matrix quantum mechanics, the barrier is one matrix. So what we're going to do in this talk is we're going to make a small step in the direction of BRSS and BMN and learn some new things about two matrix quantum mechanics. Okay, that's our objective for today. And what I'm about to tell you about was very completely 100% inspired by this very nice paper of Henry Lin that appeared actually just a couple months ago, in fact. And so what he did, he was looking at matrix integrals, large N matrix integrals. Okay, so no time, just integrals. And he showed how you could numerically essentially solve these integrals very effectively using positivity constraints, which I'll describe in a minute. Okay, and this using of positivity, there's certain quantities that have to be positive, right? So the strategy is you make a guess, you calculate something, you know that that thing is positive. If it's not positive, then your guess was wrong. Okay, and so you scan over all possibilities and you exclude things that are not positive. I'll describe it in a minute. That general strategy is what we're going to refer to as the bootstrap. Conditions about positivity. Okay, so Henry Lin showed how a sort of bootstrap philosophy could be quite efficient for large N matrix integrals. And what we're going to do, so I've been thinking about, me and my collaborators have been thinking about matrix quantum mechanics for some time now. And as soon as this paper appeared, it was clear that it was going to be very useful for matrix quantum mechanics too. And so we're going to use the same philosophy, but for large N matrix quantum mechanics. Okay, and so the strategy, which I'm going to outline, is going to involve the following. So we're going to take simple operators like x squared, x to the fourth, simple operators. We're going to relate the expectation value of these operators to the expectation value of slightly more complicated operators. Then we're going to impose positivity constraints on these more complicated operators. And these constraints are going to, well, strongly constrain the simple operators. We'll see how this works in a minute. And the upshot is going to be that we're going to obtain some new results for two matrix quantum mechanics, okay, which I believe is the frontier. I guess this is a conference on frontiers. So the frontier of matrix quantum mechanics is two matrices, and so that's where we're going to make a bit of progress. Okay. So let me just outline the plan. So I'm gonna do a warm up with just a everyday normal quantum and harmonic oscillator, and I'm going to show you how you would solve that with the bootstrap philosophy. Then we're going to do one matrix quantum mechanics, which is already solved, but this will be a check that the method, and hopefully convince you that the methods work. And then we'll move on to two matrix quantum mechanics. Okay. Now I'm very happy to take questions as I go along. And so if there are any questions at this point, please let me know. Right, so maybe to just reemphasize, it's clear, I think, and no one's going to disagree, that matrix quantum mechanics are a core problem that we need to solve if we want to understand quantum gravity and how holography actually works. And so that's the direction that we're going in. All right, so let's illustrate the methods with a warm-up example, is the anharmonic oscillator. Okay, so here's the Hamiltonian, p squared plus x squared, and then there's this x to the fourth term with a coupling g. So it's pretty simple. If you could just put the Schrodinger equation on a computer and easily find the eigenvalues. Okay, so there's nothing new here, but there's a new method. So the point here is to illustrate the method. So we're going to do the following. So there's going to be two steps. The first step, we're going to relate the expectation values of various operators in eigenstates, and then we're going to constrain them using positivity. So the way we're going to relate them is with this equation here. And so that's true in an energy eigenstate, of course, right? Because H can act to the left, it acts to the right. It gives you the energy, right? So this is just to be HO minus OH, and that's zero, because this acts here and it gives you the energy. It acts here and it gives you the energy, and so that's zero. So we're going to use this relation. This is trivial. Okay, this is definitely true. And so we're going to take this relationship and then plug in these operators: x to the s for any integer s, and x to the t times p for any integer t. So you plug the operators in, you commute them through the Hamiltonian. Okay, you basically commute the thing, and you get a whole bunch of operators, right? Because you have to commute every time you commute, right? You generate a whole string of operators. So it turns out that if you take the string of operators you get from putting this operator into here, you put that operator into here, you commute everything through, and you get all the p's on the right. Okay, and then when p squared acts on the eigenstate, you can eliminate that in terms of the energy, right? Because from the Hamiltonian, p squared acting on some energy eigenstate is E minus x squared minus gx to the fourth on the state. Okay, so you do that, and it turns out that what you'll get is a recursion relation, which is this one. Okay, so this is a recurrence relationship between expectation values of powers of x, right? So this is his x to the t minus 1, x to the t minus 3, t plus 1, t plus 3. Okay, so this is just a recurrence relationship between expectation values of operators in any energy eigenstate of this system. Okay, the energy appeared here. And so in particular, what that means is that if you fix E and you fix x squared, the expectation value, then you can work out all the other expectation values using this recurrence relation. Of course, it's normalized, right? So the expectation value of 1 is just 1. So from these facts, so suppose you know the energy and you know x squared, then with this recurrence relation, you can calculate all the higher x's, all right? Now, of course, we don't know the energy and we don't know x squared, all right? So that's where step 2 comes in. Okay, so step 2 is going to be we make a guess for the energy, we make a guess for x squared, we calculate a bunch of higher expectation values, and we see if they're consistent. All right. So step one, so let me just repeat it. Step 1 comes from this fact, which is sort of true. And you put in these operators, you commute them through, you use the Hamiltonian, and you get this recurrence relation between expectation values. Okay, that's step 1. It's very simple commuting things in quantum mechanics. Okay, so step 2 is a positivity constraint. And at this point, we're following this paper that I mentioned by Lin very closely. So it's clearly trivially true that for any operator O, if I square the operator O dagger O, that expectation value should be positive for any operator O. And in particular, I can take O to be any superposition I want of powers of x. So if I take this operator and I plug it into here, what I'm going to get is something like a bunch of C's. So let me maybe very schematically, I'm going to get something like C1, C2, something like x0, x1, x1, x squared, C1, C2 very schematically. For example, if I have x has to be positive. Okay, so for any C's I put, because of this positivity constraint, for any C's I choose, I better get a positive answer. So the eigenvalues of this matrix here have to be positive. Okay, so if I pick K, I take a sum of powers of x up to K. And so this gives me a K plus 1 by K plus 1 matrix, which is just this matrix. Okay, so that's what I wrote here. Right, this matrix here is just this matrix. Okay, this is like a matrix with different powers of x as you go up and down. The eigenvalues of that matrix have to be positive because of this condition. All right, but what we saw in the previous slide is that if I know the energy and I know x squared, then I know all the other powers of x. Okay, so the strategy is the following. We make a plot, energy, x squared. We scan over the plot. For every point in the plot, we calculate this big matrix. We calculate its eigenvalues, and we require that they're all positive. If they're negative, then that value of the energy in x squared is excluded, right? It cannot be the real values, right? And clearly, the bigger we take K, the more powers we probe, the stronger the constraint is going to be. So you fix K, you pick an energy, you pick an X squared, whatever you want. You calculate using the occurrence relation all of these X's. You calculate the eigenvalues of this matrix, and you require them all to be positive. Okay, and you get plots like these ones. So here I've got the values of so it turns out that what you find is that in this E versus X squared, almost everything is excluded except some small little dots, and each dot is an eigenstate of the quantum anharmonic oscillator. And so in this plot, I'm zooming in, right? So the big plots of energy against X squared, what you'll find is there are a bunch of little islands, okay, which are the energy eigenstates. And for quite small values of K, these constraints, and this is I think what Lin observed, that it really works very efficiently. So you can take relatively small values of K, and then look at these axes here are pretty constrained, okay. And as you make K bigger, the allowed region gets smaller, and this red dot here is the actual answer, okay. And so by the time K is 9, this is the ground state. This dot is the ground state. You really zoomed in. All that's left is this little slither that's really zoomed in on the ground state eigenvalue. This one here is the first. This one here is the first excited state. So I zoomed in on this one. Now I'm zooming in here, and you see that the energy, the expectation value of X squared, and the expectation value of the energy is extremely constrained with relatively low values of K. The higher you want to go, the more constraints you need, of course. Okay, so that's the philosophy, right? That the long expectation values of sort of bigger operators give constraints on strongly constrained expectation values of shorter operators. And so you can really, I mean, you can run this, you could code this in half an hour, right? You just have to, you put in this recurrence relationship, you scan over the values of E and X squared, you calculate this matrix, and you very quickly make this plot. Okay, there's nothing very sophisticated here.
I have a question.
Yes, please.
Hi, Sean. It's Giuseppe. It wouldn't be enough, I suppose, to just check the expectation values of X squared are turn out to be positive.
Say again?
You compute from this recursion relation all the expectation values of X to the even power. It wouldn't be enough just to see that these are positives, or do they come out positive?
No, this is a stronger. Yeah, I think this is a strong. Let's see. No, this is a yes. Of course, that's a subset, right? That's so. Let's see. No, I think that's not. I mean, that will give you some subset of these constraints, but here we're right because here we have this C, right? So we're allowing these C's. So what Giuseppe is asking is just take the operators to be you know, x squared, x cubed, and just square them, and that will give you some constraints. But this matrix of constraints is much stronger, right? Because it's for all values of C that you get something positive.
Okay.
I don't. Let me think. Yeah, I can think about it again, but I don't think it. I think these are more constraints. Yeah, because they're quadratic. Yeah, it's not like it's a linear system, right? It's a quadratic constraint. Yeah, I think that's true. Yeah. Is that good?
Yeah, thanks.
Any other questions? It's good to ask questions now because basically we're going to do a slightly more complicated version of this, but this, in essence, this is what it is. The reason it's going to be a bit more complicated is that here, what we did is that in this recurrence relation, there are no P's, right? The momentum got eliminated. And that was because every time we got a P squared, we just eliminated it in favor of the energy. But when we've got matrix quantum mechanics, there's a matrix multiplication, and you can't always get everything in terms of P squared, okay? And so we won't be able to eliminate P in the matrix case. Okay, so let's do one matrix. So one matrix, so this is a solved theory, and so this is a check of what we're doing. And so here's an example of a Hamiltonian. It's like the anharmonic oscillator, but they're traces, right? So there's a matrix worth of momenta, a matrix worth of x squared, and a trace x to the fourth. We could pick other
Excuse me,
powers.
may I ask you what
Yes.
happens if you take a cubic power here, non-positive definite case?
Yeah, so I think we didn't. I suspect it will not be a happy thing because probably won't converge because these dots will just go down. I don't. You know what? So actually, Henry Lin did look at this question for and I don't remember the answer for the matrix integral, but we did not look at it yet. You'll see in a minute what happens. In the matrix theory that we're about to do, we're going to be at infinite n, and it's actually going to be a continuum of states, and we're going to have to sort of minimize to find the ground state. And if the potential is unbounded below, it's just going to be useless. So I think that the way we're doing things in the matrix case, with an unbounded potential, I think it's not going to work. But for the quantum mechanics, it may be that one can find some metastable states. I'm not sure. I haven't thought about it. Right. I mean, the problem is that it's unbounded. But maybe you can still find some things. I'm not sure. Because a large n, they're infinitely long-lived metastable states.
And matrix model, you can find solution. In principle, you can find solution. Maybe we can discuss later. Okay. So
right. So at large n, there are sort of infinitely long-lived metastable states, and it may be that we can find these, but I haven't thought about it. Probably you can find them, but I'm not. There may be some subtleties. I'm not sure. Actually, okay. Let me not speculate online, but yes, I suspect you can find the metastable states. Yeah. Any other questions?
Is it probably it's possible to check whether the solutions, explicit solutions, how they how they fit to this positivity domain? Was it done actually?
Sorry, I didn't quite hear the question. Could you say it again?
Well, if you just solve the equation, so just it's possible to find this matrix element of x squared explicitly and to see how it fits the positivity domain.
Yeah. Okay. Good. That's right. So actually, yes, there. Let's see. Very roughly, yeah, very good. So actually, in Henry Lin's paper, there is a discussion of something like that. And so if you imagine the sort of the eigenvalue distribution, some semicircle, some kind of semicircle, and then the sort of the functions that come close to bounding this constraint are sort of like zero modes, and they're functions that are basically zero inside the eigenvalue distribution. And so yeah, there absolutely is a connection between the eigenvalue, the distribution of eigenvalues, and this constraint. If that makes sense.
A quick question, Sean.
Yes. Hi, Sumit.
Hi. So do you take the coefficient of trace x squared to be always positive?
Oh, good. Yeah, because we were mostly interested in the two matrix case. Let's see. Yes, we literally that is correct. And what we did, we literally took this Hamiltonian that I just wrote down with positive g, g equals 1. In fact, no, OG. We scanned over g, and we did not consider negative x squared. I don't see any obstacle to that. And that indeed there may be something interesting with these disconnected solutions and so on. Yeah, we haven't explored the full space of possibilities of one matrix.
Okay.
Right. You're asking, so Sumit's asking about this, a potential that looks like this, right?
Right.
And indeed, maybe there's something interesting with there being two minima, and I have not.
Yeah, because I was going to ask whether you can take a limit of this and go to the inverted oscillator.
Yes, I quite possibly. Yeah, yes, Well, let's see in a minute how things work, and you might get a sense of some of the challenges to doing that. But indeed, there's probably more to explore in this one matrix case that we didn't do. Yeah. Good. Yeah. So let me describe it, and maybe you'll see there's one that you'll see the subtle point with unbounded potentials. Okay. So given this Hamiltonian, let's see. So we're going to do a similar strategy. So the first step is to relate expectation values, but we're not going to eliminate P. Okay, so P is going to be there. And so we're going to use, but we have an extra type of equation. So first we have this one, which is just the same as before. So these are energy eigenstates. Actually, this is also true in Gibbs states. So like thermal states this also works. So whenever the density matrix commutes to the Hamiltonian, we will have this, but let's say eigenstates. And so, for example, if we take the operator to be trace xp, then this relationship gives sort of this virial theorem, which is a relationship between p squared, x squared, and x to the fourth. Okay, that's an example. Now, we're going to look at gauged matrix quantum mechanics, which is normally what is of interest. And so there we have another whole bunch of constraints. And so the generators of SUN, right? So there's an SUN symmetry that we want to gauge. And these are the generators. This extra term here is because of operator ordering stuff. So these are the generators. And because the state needs to be gauge invariant, we can impose this constraint that for any operator O, we multiply it by G, and G has to annihilate the physical states. And so this is also true. So the simplest case of this is just to take O to be the identity. So trace of G should be 0. And so, for example, if you combine this constraint with this constraint, now putting x squared here, you find that trace xp equals minus trace px equals that. Okay, so this is an example. These are simple examples of getting two relationships between expectation values. But you put in more complicated O's and you get more complicated constraints. So that and philosophically the same as before, but we're using this extra constraint here, which is gauge invariance. So then now, okay, this is the bit where it's not as nice as the anharmonic oscillator, because we don't have a closed form recursion relation. All right, it may exist, but we don't have it. So you pick a set of operators. So for example, here I pick the identity x squared, x, and p. Right, I pick a set of operators. Then I make this matrix. Okay, so I make a matrix of these operators, and these are all, and I write down these expectation values. Right, so clearly this is like x and x squared. So I have x to the fourth here, x and x squared, x and p, so px and so on. Okay, I write down this matrix. This matrix needs to be positive. Okay, for the same reason as before, because it's a sort of a square operator, a square of expectation values. A matrix of expectation values that you get by squaring up by operators. So, so we're going to impose positivity on this matrix. I mean, of course, we're going to have much bigger matrices. I'm just showing you an example. And before, I showed you how we could relate, right? Before, we related p squared in terms of x squared and x to the fourth. And we also got expressions for px. So in this matrix, I can solve this guy, and this guy. I can relate to these ones. Okay, and so then I have fewer operators than constraints, right? So I diagonalize this matrix. I impose that all the eigenvalues are positive and well, non-negative. And so, for example, one constraint you'll obtain is this one. Okay, so this is some constraint. It depends on G, the coupling between the x squared and the x to the fourth expectation value. All right, so the strategy is going to be, we take a big set of operators, we get a huge matrix, we relate as many of the entries of the matrix as we can, and then we impose positivity, all right, and see what happens. All right, so we do the following. We take all strings of x's and p's of length less than some length L. So there are 2 to the L such strings, right? Because you have xp, xx squared, px, so on. Then you get a big matrix, which has 2 to the L squared, so 2 to the 2L entries. So that's a big matrix of expectation values. Then, so we impose positivity of that matrix, and then we write down all relationships between these expectation values of the types we just discussed. So we put all the operators into this equation and into that equation. And furthermore, we have one more constraint, which is large N cyclicity. So if you just have numbers, not operators, then trace of x p cubed would be the same as trace p cubed x. These are quantum operators, so when you move them past each other, they don't commute, and you generate some extra terms. And these include multi-trace operators, which we don't want to deal with. And so this is the place where we use large N factorization, and so we can factor these. So this now, these cyclicity constraints are quadratic constraints between expectation values, okay? Because they have things like this, right? And so and then those are the equations. So once again, huge matrix, positivity of the eigenvalues of this matrix, and 3 types of relationships between expectation values, right? From the Hamiltonian, from the gauge condition, and from cyclicity of the trace, right? So that, now, if you do that, you still get a big parameter space that's left, okay? And you find it as a continuum of allowed energies. And that's okay, because we're at infinite n, and these matrix quantum mechanics do have a continuum of energies at infinite n. And we expect the lowest of these energies to be the ground state energy. So what we do is we have this big constrained space, okay? And we do gradient descent, just try to minimize, we try to find the minimum energy, have a big space of expectation values, and we minimize the energy within this space of expectation values that's allowed by these operator and positivity constraints, okay? So we do this minimization numerically. So that's an extra step, okay, that we did not have to do for the harmonic oscillator. And this is where I think things may get a bit complicated if your potential is unbounded below, okay? But it may be possible, but that's may not be happy. And so here are the results. So for one matrix. So what we see here, this is the energy against the coupling G. This line is the exact result from the large N solution of the theory. And what we see is that already by L equals 3, so that's considering all strings of 3 x's and p's. Of course, the matrix then has 6. Okay, so expectation values of all operators up to 6 x's and p's is basically on top of the exact solution. Okay, and it stays there for L equals 4. All right, and we can also here's trace x squared against G. And again, once you get to L equals 3, so remember L equals 3 is the length. It's basically on top of the it's on top of the exact solution. Okay, so this we can quite quickly, fairly quickly recover the known solution. All right. Now, an interesting thing here that's a bit different from what I did before for the oscillator is I never used the Hamiltonian. Okay, I didn't use the fact the energy doesn't appear. So we only use this commutator of H with O. We never actually act with H on the state to get the energy. So we can also, so in this plot, so this is now the energy, I'm plotting it as a function of the energy, right? So I do, and this is x squared. So I do the following. So we have this big space of allowed expectation values. If I go to the minimum, I get this curve. But if I go away from the minimum, then I'm at some finite energy from the ground state. And then I ask, fix this energy, so that add the Hamiltonian being constant, fix the energy and ask, what's the range of x squared that's allowed at that energy? And that's this plot, right? So I fix the energy, that's the fixed energy. And this is the range of x squared that's allowed at that fixed. So this bounds x squared in excited states. And so L equals 3, if you make L bigger, the range gets smaller, right? And this dashed line is the exact answer for the thermal state, which should be certainly an allowed state. So you fix a temperature, at that temperature you calculate the energy, and you calculate x squared, and that gives you this curve. This is all in the singlet sector of the matrix quantum mechanics. And so here we see that this bootstrap, I mean, these numbers are, reasonably constrained. We can also constrain excited states here, okay, like this. There's a continuum of excited states, and their expectation values are bounded by these curves. All right. So my main point here is to try to convince you that this method works. Okay. The step you might be a bit worried about is that you have to do this extra minimization, but it seems to work quite well. So any questions before I go on to 2 matrices?
Sorry, I have a question.
Yes.
So in matrix quantum mechanics, a very interesting sector is the non-singlet sector, because if there are black holes, it is expected that they should appear in this in the non-singlet sector, right?
Yes,
So
absolutely.
can you actually apply anything to the non-singlet sector?
So we have not done it, but I shouldn't. I don't see an obstruction in principle, and I think that would be very interesting. Very interesting question. Yeah.
Okay, thanks.
Yeah, we haven't done it, but yeah, I think that indeed. And when I said this model solved, I should say I think there still are some mysteries, in fact, regarding how black holes work in this theory, and maybe this is the interesting method to approach that. Thank you.
I have a question which is
yes,
maybe also related to the previous part. If you would consider infinitely long operators, would it mean that positivity domain will shrink to a single line?
Yeah, wonderful. We don't have a proof of that, but I believe that is probably true. Yeah. So the question is whether this method converges, right, as you make L bigger, and I suspect it does, but we haven't proved that, partly because of this picture that I drew very briefly before, that if you have a eigenvalue distribution, and what you're sort of really doing is you're looking at the space of functions that kind of vanish identically inside this when you integrate it against the distribution, because those give you sort of the zero. They saturate these bootstrap constraints, and the bigger you make the order of the polynomial, the better you can. The more precisely you can get these sort of zero modes. It's a little bit more complicated because we have P as well as X. So anyway, we haven't proven that, but it looks promising that it should be true.
So in this way, positivity inequalities would go to equality, right? And they would be just saturated. So positivity.
I think something, yes, I think something like that should be true. Yes.
Yeah.
Yes.
Okay.
I think that's right. Yeah. Thank you. Yeah, yeah. Very good. Okay, so now what hopefully I think we were most excited about. So let's do two matrices. So this is the sort of simplest two matrix theory. Without this mass term, so without this term, I think this was first studied by Hopper in the early 80s, maybe earlier, I don't know. It's useful to have this mass term as well. And so this is the simplest two matrix quantum mechanics that you can write down. And so now you have this commutator squared interaction between the two matrices. All right. The numerical method is exactly the same. So we write down, as for one matrix, we write down all strings of length L. But now we have px, py, x, and y, right? So there are 4 operators that you could put at every point in a string. And so there are 4 to the L possible strings of length L, and the matrix is now 4 to the 2L. So unfortunately, it's a numerical method, and we're fighting against an exponential growth. But these constraints do cut things down a lot. So we impose the same constraints as before: the Hamiltonian constraint, the gauge constraint, the cyclicity constraint. And also, to reduce the number of equations, I believe not completely essential, but we did it. We also looked at just rotationally invariant wave functions. So that should include the ground state, you would hope. And so in rotational invariance, we impose this extra constraint on the operators that the expectation value, actually this just says it's an eigenstate of angular momentum, but it includes 0 eigenstate. Well, this is the generic, so this model has an O2 symmetry, right? It has SUN gauge symmetry, but it has an SO2 global symmetry. You can rotate the matrices, and we're restricting to eigenstates of that, just to reduce the number of variables. And then we just do the same thing. Just quickly before I show you the results, I have 2 more slides. Now, we don't know the answer, okay? That's the whole point. This is not a solvable model, okay? So, but we'd like some kind of check that what we get is not completely crazy. And so I think we did something that I thought was quite nice. And so I'm gonna show you quickly a Born-Oppenheimer wave function. Okay, so I'm gonna write down a wave function that's a Born-Oppenheimer, and what this wave function will give us is both an upper and a lower bound on the ground state energy. And that's Born-Oppenheimer gives you that. So you can use Born-Oppenheimer as a variational wave function, and that gives you an upper bound. And also, if you use it like you would in chemistry, you also get a lower bound. So let's see. So what we do is I'm going to for the Born-Oppenheimer, this is just for the check, okay? For the check of our results, I diagonal, so this is not the true ground state, okay? This is an ansatz. We diagonalize one matrix, and then with that using the gauge invariance, you can do that. And then we put the other matrix, the oscillators of the Y matrix, so we diagonalize X, and we put the Y oscillators in their instantaneous ground state. So you fix X, and then you put the Y in the ground state. So then the wave function looks like this. There's some wave function of the X's, and then the Y's are all in their harmonic oscillator ground states where their frequencies depend on X. As some of you may be familiar, this kind of xi minus xj squared, that comes from the commutator term, right? This comes from so xy squared trace becomes xi minus xj squared yij squared. Okay. So anyway, so this is so the function of this wave function is that now it reduces to a single wave function of eigenvalues, and we can solve those using the techniques from the 90s or earlier. And by solving that, we get a rigorous upper and lower bound on the ground state energy from single matrix techniques. Okay, and we're going to use that to check the results. Very good. So here are the results for two matrices. So I guess these are our main new results. So as you can see, it's exponential growth. So we didn't go to L equals 5 this time, although it's probably possible. And so this is the energy against G, I guess sort of the TÜV coupling. This is the expectation value basically of X squared against G, against the TÜV coupling. And this is the expectation value of the commutator against the coupling. Pretty converge between L and 3. So we have these curves, the commutator mass, and this one is for the energy. And these dashed lines are the Born-Oppenheimer upper and lower bounds. Okay, and so that looks like this L equals 4 result is at least somewhat I'm optimistic that it's quite close to convergence. Okay, although ideally we should have L equals 5 as well. L equals 4 is already enough to get. So actually, I was a little bit surprised about how good these Born-Oppenheimer bounds were. Okay, they constrain the ground state quite strongly, and our numerics are within the allowed bound. Okay, so so I think these are new results on the ground state energy of two matrix quantum mechanics at infinite n. We also have the commutator and the X squared. Okay, so just to wrap up, so what the main message, again, once again inspired by this nice paper by Lin, is that positivity constraints give a powerful approach to matrix quantum mechanics wave functions. I showed you some new results for two matrix quantum mechanics, which again is I think sort of the frontier of matrix quantum mechanics. I think that especially if we use this rotational invariance, it should be possible to go to more matrices and add some fermions. I think it's certainly possible in principle and hopefully in practice. And if we can do that, then I think that'll be very exciting because we'll be able to characterize the BFSS ground states. Another direction are non-zero temperatures in multi-matrix quantum mechanics, because there you will directly get to black holes. Right? With one matrix, you need to go to the non-singlet sector, but as soon as you have two matrices, you're already in the non-singlet sector because you can't diagonalize both of them. And actually, there is quite a big existing literature on Monte Carlo simulations of finite temperature matrix quantum mechanics, and maybe we can reproduce or even improve those results using this method. And of course, this will also give a window on black hole microstates. And finally, maybe looking further ahead, these are simple. These are rather simple properties. Trace commutator of xy, trace x squared, and the energy. And of course, be very interesting to understand more fine-grained. I mean, the power of this, as opposed to Monte Carlo, is that it's quantum, right? We're looking at the quantum states. This is not some thermal state. And it would be great if we can somehow get access to the more fine-grained structure of the wave function, such as entanglement and so on. All right, that's all. Thanks very much.
Thank you very much for your nice talk. Questions, please?
Can I ask? I didn't quite understand how you get a lower bound from a variational wave function.
Oh, okay. So I went. It's a textbook, Giuseppe. It's a chemistry. Okay, so let's see. So yeah, no, very good. No, actually, we were confused also for a long time. So you get both an upper and a lower bound. So let's see, how does it go? So right. So the full wave function is some wave function of the eigenvalues times some oscillators for the y's, right? A bit like this. You can see this, right? What I'm writing.
Yeah, yeah.
So the one thing you can do is just take this to be a variational wave function, and that will definitely give you an upper bound. Okay. Another thing you can do is write down some H effective for the x's, which is basically the Hamiltonian restricted to x. So like the derivative terms on x, right? The x derivative part. And then you add the ground state energy of these oscillators, which as a potential. Okay, so you put the y's in their ground state. That generates an effective potential for the x, right?
Mm-hmm.
And you get this Hamiltonian. And it turns out that the ground state of this Hamiltonian is a lower bound. It's not, when you do the variational, when you do it with variational, there's actually an extra term that gives you an upper bound. But if you just restrict to this, to just the ground state energy of, because there's some cross terms, right? But so suppose I just take this ansatz and I plug it into the Hamiltonian and I calculate the expectation value. There are three types of terms. They're when the derivatives hit the psi, they're when the y derivatives hit here, but there are also terms where the x derivatives hit these omegas. Does that make sense?
Yeah.
If you include the terms where the x derivatives hit the omegas, you get an upper bound. If you don't include those terms, if you only include this energy of the omegas, then you get a lower bound. It turns out you can prove that it's true.
Okay, thanks.
Okay.
So yeah.
More questions, please?
Can I ask a question?
Sorry.
Yes, of course.
Thank you for the very nice talk. The recursion relations you're using, you can think of them as some sort of Schwinger-Dyson equations. And I was wondering to what extent using such type of equations, even for higher theories, you can get similar results.
Wonderful. Let me a couple words. So actually, Henry's paper, this paper on this one on the matrix integrals, he very explicitly used Schwinger-Dyson equations. I think what we're doing is not quite that, because the problem with, at least, I mean, maybe it's possible. So the problem with the Schwinger-Dyson equations, like taken literally, is that they involve integrals over time, right? In the quantum mechanics case, and what happens with, now in principle we can do time evolution, but as you know, operators grow complicated over time, right? These are chaotic systems. And so if I time evolve an operator, it gets long. And those are operators that I would expect to be difficult to capture with this method, at least the way what we're doing now, because right, you need a bigger set of trial operators to constrain long operators. So we did not know at this point how to use Schwinger-Dyson in the quantum mechanics case in a non-trivial way. It definitely did work in the matrix integrals because there's no time, but
No sounds, please.
well, I don't know if it's the same question, but I mean, for example, we can use a Gibbs, we can put in the thermal states. Is that what you, is that maybe what you mean? So
not really, but well, that could be one interpretation of what I'm asking. But suppose you have a Euclidean, I mean, one-dimensional or two-dimensional field theory.
I mean, let's see. So what we're doing here is looking at wave functions, right, at states. So I mean, if you define those, I mean, those are sort of Lorentz, I mean, you can define them by the Euclidean path integral. So that's why I think what that amounts to would be considering something like the thermal state, right? So because we're not
state or the ground state.
well, but I mean, sorry, let me see what you, good. You could do the following. You could certainly take different polarizations of different quantizations. I mean, so it's a question of what you mean, because this is all very operatorial, right? So we have a Hamiltonian, right? I mean, you want to put a minus sign. What do you want to do with a Hamiltonian?
Well, if I have a Euclidean field theory, I cannot talk about the Hamiltonian, right?
Right. So then exactly. So I think it's.
It has to be some other operator. So what you're saying is probably that it's not so obvious.
Yeah, I'm not. Well, it would depend exactly what you want to do. I know maybe this is not what you had in mind, but let me iterate one thing that I think, because it is nice. In all these constraints we write down, like this one, and they all work for this expectation value could be trace of anything. A could be trace rho A, where rho is e to the minus beta h. Okay, so we're definitely we don't use in this matrix, in this, for example, this stuff anywhere the fact that they're eigenstates. It also works for these mixed states that commute to the Hamiltonian, like the thermal density matrix. And that's why here, for example, this line, this is a thermal line. So that's a sort of Euclidean-ish kind of quantity is tractable. So thermal states are tractable. If you tell me more, probably Euclidean stuff is possible. I haven't thought about it.
Okay, thank you. I think you already said more than I wanted. Thanks.
More questions, please?
Yeah, a quick question. So staying with two matrices, is it possible to add enough fermions and hope to get a moduli space or threshold bounds?
That's so very good. You mean add fermions to this theory?
Yeah.
I forget if there's a supersymmetric one with two or not.
You can
there's definitely with three. I'm sorry?
You can construct the supersymmetrical generalization of this model.
Perfect. Okay, great. So yeah, so we are thinking about.
My question is there enough supersymmetry to have?
Yeah, so I know that I can tell you. I know that for 100% sure with three matrices and fermions, there's definitely a moduli space, and it may quite possibly with two. I don't know. So with three matrices is what we called it the mini BFSS, but Tarek called it mini BFSS. So, but let's see. But even with two, let's say you could supersymmetrize this. I mean, things will get a bit complicated because there's the fermionic matrices in addition, right? Mm-hmm. On the other hand, you do have stronger constraints, right? Which is like the Q on the state is 0.
Right.
So we're just starting. We haven't got very far. So in principle, I don't know whether the stronger constraint compensates for there being a bit slightly more degrees of freedom. I don't know that yet.
That would be very interesting to see.
Absolutely. I think there are lots of. And I should just stress that the code that we used is on the archive. There's a link to the code. There's nothing very magical happening, right? I mean, it's just being systematic with constraints and stuff. And I certainly hope that it's possible to add fermions.
Thank you.
Another question. If you have in mind the holographic interpretation, presumably you want to find very highly excited states, no, that have a semi-classical interpretation.
Well, I mean, the ground state should have a ADS interpretation, no, or ADS, or something. Yeah, so I'm not sure they're very highly excited, right? I think certainly in the one matrix case, the ground state is, it's very simple, of course, but the one-dimensional space-time is already the ground state, right? So excited states are certainly interesting, but probably harder, but maybe doable. But I think the low-lying state should already have quite a lot of information, I think, holographic information.
Yeah, well, I was thinking like in the BFSS where you get solutions where, the matrices do not commute and they form a representation of the rotation group.
That would be, no, I think you mean maybe BMN, right?
Yes.
Yeah. So definitely, yeah, BMN, that would be great. And actually, let me quickly advertise another paper. So Han and I wrote Shiji and I wrote a previous paper, Han and me, using neural network wave functions. I mentioned this as variational wave functions. And actually there we did capture, so what Giuseppe is talking about is a fuzzy sphere. So you can find that the matrices, so you need at least 3 matrices. So this what Tarek called the mini BMN model. So you can have three bosonic matrices plus supersymmetry. That has a fuzzy sphere solution. And actually we found it in the wave function in this earlier paper. And probably we can use this method too, but there's one more you need at least one more matrix, so we haven't done it yet. But sorry, that's still the ground state, is my point, right? These fuzzy spheres are still ground states.
Oh, okay.
Can I ask also a question?
Yeah, please.
So in the BFSS, there is the problem, right, of the flat directions, right, in order to find the ground state. Do you expect that your method will converge if you have flat directions? Or?
So that's a very interesting question. So BFSS does have a normalizable ground state wave function. Okay, actually, this comes back to Shumit's question.
Yeah.
Some of the for example, with the mini BFSS, so that's three bosons plus supersymmetry, that doesn't have a ground state. It has a moduli space. Okay, but actually BFSS has an honest ground state. Now that ground state does have power law fall-offs. It's quite an extended ground state, and it's conceivable that so certainly, for example, in Monte Carlo studies, that's a pain. Okay, that makes things difficult. I don't know at this point whether that'll be a problem for this method or not. But BFSS does have a normalizable ground state. So these classically flat directions get lifted despite the supersymmetry. They do get lifted for BFSS, but not in other cases. We don't know. So I don't know if that may or may not be a difficulty. I don't know.
More questions, please? Maybe I will ask simple questions. What happens with your method if you don't take large n limit, just take 2x2 matrix or 3x3 matrix? Do you expect something interesting?
Yes. So I think very good, fantastic. Good, thank you. Good. So the only place where I used infinite n was in here when we did this cyclicity. Okay, so these give us some extra constraints between operators, and so of course matrices normally they're just cyclic, but these operators you have to commute them through, and you generate these other operators, and these include some multi-trace terms, but at large n you can factorize them. So if we do not use large n, but we want to stay within the space of single. Well, we have 2 choices. You can either go to multi-trace operators. Okay, that's fine. And for n equals 2, 3, like 2, 3, 4, we can probably just do it, right? So n equals 2, 3, 4, I think should totally work. N equals 100, that may be trickier. And so because for small n, we can probably just ignore this. We don't have to impose this cyclicity constraint. It just made things more powerful, right? The more constraints, the better. So for small n, you probably, yes, that's right. It might be that you can get away with not imposing this cyclicity constraint. You can do it. What's a bit harder is, suppose you ask me, what about the 1/n corrections to the infinite n limit? And that's a bit trickier because there'll be some multi-trace operators that appear in these constraints, and I'm not sure what to do with those. But yeah, fixed n 2, 3, 4 I think should work.
Okay, thank you.
Actually, it's a good point, because there are that's a good point actually, because for BFSS and some of these other models, people solve them explicitly with small n, and we could check our results maybe against those.
Okay, thank you. More questions, please? Okay. There are already many questions. Let's thank Sean once again. Thank you very much.